Next argument is about nominal stress and true stress. The true stress is a little different from the stress that we have argued so far. We learned that when calculating a stress in a material, the load applied to the material should be divided by the cross-section area. You may notice that the cross-section area here is actually the area under no load acting on it. This stress is called the nominal stress. In reality, however, the calculation is not strict. The cross-section area changes as a function of time as the material is stretched. Now, we assume that the original cross-section area is A0, in which no load is acting on the material. In the previous argument, the external load was divided by this original cross-section area, A0, to calculate the stress. This value has been defined as stress, and various problems were solved based on this definition. In reality, however, the calculation is not strict. The cross-section area changes as a function of time as the material is stretched. Now, we assume that the original cross-section area is A0, in which no load is acting on the material. In the previous argument, the external load was divided by this original cross-section area, A0, to calculate the stress. This value has been defined as stress, and various problems were solved based on this definition. However, if you stretch a material up to a fairly higher strain, the material becomes thinner, significantly reducing the cross-section area. We may here recall the story of the Poisson's ratio, which also argued about the reduction of cross-section area due to the stretch of a bar. The illustration described the deformation of a bar stretched from the initial length of L0 to final length of L at force P. Here, A0 is the initial cross-section and A is the cross-section at the moment during the deformation. You may notice that we need to divide the load P by the reduced cross-section area A in order to calculate the stress more precisely. This stress is called the true stress, defined by the following equation. The quantity which we have called stress so far has been the nominal stress. After getting familiar with this explanation, you may think that the stress, or nominal stress, which we have been using, is a bit rough. But it is not actually the case. Following arguments include this point: situations in which nominal stress and true stress should be used respectively. The true stress is the load divided by the real cross-section area of a moment. When the change in the cross-section area is small, the behavior of the material can be well approximated by using the nominal stress. So, the true stress is used only when the change in cross-section area is large. When is the change in cross-section area significantly large? We are considering about this with respect to the stress-strain diagram mentioned earlier. When a material is stretched and its strain increases, plastic deformation starts to occur. True stress is used in the plastic region, where the elongation is fairly increased. Once the plastic deformation starts, Poisson's ratio, which defines the relationship between longitudinal and lateral strains is no longer valid. When Poisson's ratio is no longer valid, we cannot calculate the cross-section by using the Poisson's ratio. To calculate the cross-section area after plastic deformation, we assume that the volume is constant. In other words, the original volume is given as the product of the initial cross-section area and the length. The volume after the deformation is given as the product of the cross-section area and the length at that time. We use the rule that the volume is constant to modify the cross-section area. This assumption allows us to calculate the true stress. So far, we have learned that the true stress is defined as P over A. This equation, derived from the assumption that the volume is constant, can be used to eliminate A. So, we get the equation. We now focus on P divided by A0 in this equation. This is the definition of the nominal stress. So, to calculate the true stress, the equation is derived. By using this equation, you should notice that we can convert the nominal stress to the true stress. So, once you get a value of nominal stress in the result data of a tensile test, you can convert the nominal stress to true stress with length of the material.